Before I begin, I'd like to thank Interlligent for giving me this opportunity of a talk. It's a great pleasure for me to be here today. And secondly, of course, I'd like to acknowledge very deeply my ex-student Aditya Poluri, who I'm very pleased to say is now an assistant professor at IIT Kanpur as of this last week actually. And since the summer, in his place, I've had Asha, who's sitting at the back there, who's joined me as a postdoc to continue our journey on these contiguous mode power amplifiers in class BJF inverse into the Ka band and beyond. Now, let's look at a bit of good news first. The International Energy Agency has just revealed that the global CO2 emissions are likely to peak this year, but we should be conscious that the wider ICT sector driven by telecoms networks and data centers could increase to 14% of global CO2 by 2040, up from 3 to 4% today. And this is one of the reasons why the telecoms companies, especially in Europe, are putting sustainability at the top of their agenda. Now, there are three types of emissions that happen in a network. Scope 1 emissions are those generated directly from burning fossil fuels. Scope 2 from purchasing energy and heat. But it's the Scope 3 emissions caused by downstream and upstream activities, such as the energy consumption of suppliers that constitute about 2/3 or sometimes even 90% of a telco's total carbon emissions. So most telcos have begun to take ownership of this. And this is one of the primary motivating reasons, therefore, to look into this topic that I'm going to speak about today. For those of us who are climate change skeptics, there is a very good incentive here. The energy costs can account for as much as 40% of a network's operating expenses. Now, cellular network is estimated to consume 100 terawatt hours of electricity per year, and about 57% of that is attributed to the base station. If you look at various types of base stations, the power amplifier consumes about 34 to 63% of the total energy. So therefore, it's a very strong incentive for us to look into efficient designs. Now, the art of designing a power amplifier is nothing but trying to ascertain the input and output matching impedances that would maximize the linear power and the gain and the efficiency. Not only that, I mean, you can determine the impedances, but it's quite a challenge then to actually design the matching networks and to deliver them according to the prediction. Besides this, of course, we also need gate and drain. We also need gate and drain biasing circuits. Not only to power out transistor, but we also need to make sure that the RF circuit does not veer back into the DC supply. Now, historically, it's been a traditional battle that designers face, and that's not recent. It's always a question of a trade-off between the linearity and the efficiency. Now, this has been going on for decades since the invention of the PA, but it's getting more problematic because as we go to higher and higher frequencies, the modulation schemes get more complex, and therefore there is a much bigger demand on linearity and efficiency. Now, an amplifier is a normally on high power transistor, which is biased at its Q point, VGSQ, IDSQ, and there's a really simple answer to why this trade-off exists. We can see here in class A, it's biased in the central portion of this linear region of the characteristic. So we can see that it faithfully reproduces the input signal at the output when it is in class A. But if you look at an amplifier biased at threshold or closer to threshold, we can see that only half of the wave is available at the output. And this waveform clipping results in high non-linearity. Of course, in class B, we assume that all of the harmonics are filtered out. We can then define the efficiency of an amplifier by how much output RF power we are able to achieve for a given DC power, input power, which is nothing but V dsq times I dsq. We can rewrite it in this form. And based on whether alpha is 2 or pi, we get class A or class B. So we can then plonk this back here, and that gives us a theoretical class A efficiency of no more than 50%, which is the most linear. And then the class B is 78.5%, which is pi by 4. Now, somewhere in the late 80s, Cripps proposed this load line concept, where he said you can present an optimum resistance R opt at the current generator plane of the transistor, and based on this slope or the value that you present, you can either get a maximum output power which maximizes the current swing, obviously at a cost to efficiency, or you can have a lower current swing with higher efficiency. So it's not just a trade-off between linearity and efficiency, it's also a trade-off between the output power and the efficiency. Now, traditionally, the more current you have flowing through your amplifier, the higher is the power dissipation. And it's always been the strategy that if you operating at higher voltage is a much better way to deliver higher power than operating at higher current. Ideally, what we want is to have the power dissipation to be 0 inside our transistor and maximum on the load. This brings us to the concept of waveform engineering, which was also pioneered at Cardiff University. And if we look at our efficiency here, we can see that if we want to increase the efficiency, we want to reduce our input DC power. And that input DC power is nothing but the heat dissipated in our transistor and all of the power that is contained in our output fundamental as well as the harmonics. So we want to minimize these two terms, the heat and the power in the harmonics. Now, heat can be minimized by minimizing the overlap between the current and the voltage waveforms. And if we want to minimize the power in the harmonics, we can look at this expression here. It's Vn In times cos phi n. So if Vn equal to 0, we get a short circuit. If In equal to 0, we have an open circuit. And when phi n is plus or minus 90 degrees, we can reactively terminate our impedances here, either inductively or capacitively, in order to make this cos phi n term 0. And this brings us to higher classes of operations such as class F, F inverse, J, or E. Now, let's look at this concept further. Here is the total voltage waveform, and in dashed line is its fundamental. Now, if we inject a second harmonic frequency into this load in an arbitrary fashion, what we see is that we get an increase in both the maxima as well as the minimum of the waveform. And what Cripps showed is that you need to adjust the phase of this second harmonic in such a way that this minimum will graze the knee voltage. And that's when you get the maximum benefit of harmonic tuning. So this brings us to the first continuum mode, class J. So here in black is the normalized current, which is a conventional class B waveform, and the blue is the voltage waveform in class B. What class J does is that it will shift this voltage waveform to peak either to the right or to the left by adjusting this parameter called alpha. And what that does is you can see that it minimizes the overlap on one side between the current and the voltage. But on this side, we can see that the overlap increases. And therefore, the efficiency of class J is the same as that of class B. There's no benefit of efficiency, but what it does is that it gives you a wider range of impedances to design, so it makes it easier to design. Now, class CCF inverse is a current-based manipulation. And if we take any sine wave and we remove the second harmonic component of it, it becomes a square, as shown in this red curve here. And so this red curve corresponds to class F inverse. In continuous class F inverse, we can make this peak either to the right or to the left. And at the same time, we shift the voltage waveform to a maximum of about pi by 4. And what that does then is that it reduces this overlap between the voltage and the current and thereby increases the efficiency to 91%. Now, both these modes require a short at third and higher harmonics of the voltage. Now, this class BJF inverse, which we published in 2019, the voltage waveforms of this class lie between that of class J and class CCF inverse. The third harmonic is 0. In terms of current waveforms as well, BJF inverse lies between that of class J and CCF inverse. And we can see here that class J has both the fundamental and the second harmonic, but CCF inverse has, of course, a little bit of both the fundamental second harmonic as well as the third harmonic of the current. And this is possible that by adjusting this parameter K that we have introduced in our formalism, what we do compared to CCF inverse is that we make this peaking a little bit smoother compared to CCF inverse. But the most important point here that I want to make is that we always need a little bit of this third harmonic in order to achieve these waveforms. So these are the load impedances for BJF inverse on a Smith chart. So this point here represents class B, and class J is represented by this arc of a circle here in blue. And depending on whether alpha is positive or negative, you get this J star or class J. At this end is class F inverse, which is again a dot impedance. And the line in brown represents the continuous class F inverse. And class BJF inverse is called a contiguous mode because it occupies this entire region in between that straddles these two classes. So you can have your impedances anywhere in between in this region here, meaning that you can make it more linear towards class J and more efficient towards class CCF inverse. And ideally what you want to do is to try and choose your region so that you can do the best in terms of both these parameters. The second thing, of course, is that your second harmonic impedances for BJF inverse span the entire circle on the gamma equal to 1 circle on the Smith chart, unlike CCF inverse. So are we the only ones with a contiguous mode? Not not really. There are these other 5 or 6 other classes that have been reported in the literature, out of these 5 of which are from the Far East. And this one, I believe, is from Ganucci's team in Canada. Now we can see that, class BJF inverse lies right in the center of these, all of these other classes. And there are 2 types you can see from reading here. Either they are based on class F, continuous class F, or class F inverse. So we thought also that we would like to compare BJF with BJF inverse. And what you can see here is that the series of continuum modes here has a much smaller design space compared to BJF inverse. That means, we have a much better tolerance in terms of impedance mismatch and a higher yield. They roughly have the same efficiencies, and that's because the current is higher in SCM compared to BJF inverse, but the overlap between the current and the voltage is less for our class, and so these 2 trade off with each other. Now, when we go to higher frequencies, what are the requirements of the device in order to be able to design in this class? The first thing is the FT, which is nothing but the gain bandwidth product. If we try to operate the device beyond its cutoff frequency, there is no gain. And if the third harmonic frequency is greater than FT, then there is no I3 present. So as I3 decreases, the current waveform becomes less square. So it's actually this width of the current waveform which minimizes this overlap between the voltages, and that is the one that actually gives this efficiency benefit. And we can see here that I3 goes down. We can see that this curve becomes more and more sinusoidal. So for K, I3 is not equal to 0, and that's what we need for BJF inverse. And if K were to be equal to 0, we would just get class BJ. Now here's a comparison of 2 mimic technologies here. The first has an FT of 35 gigahertz and the second at 105 gigahertz. And in this process 1, we can see that there is no I3. So although we see this kink in the current characteristic, if you look at this 2-dimensional region on the Smith chart, you can see that the P1 dB, which indicates the linearity, is at the same end of the Smith chart as the PAE, which is actually supposed to be more towards the F inverse end. So this means that there is no manipulation which is taking place in this particular process. On the other hand, in this particular process, you can see that the P1 dB area, or the region of high P1 dB, is distinctive from the region of high PAE, which is what we want in BJF inverse. Now, what is the second requirement of the device? That is the output capacitance, CDS. Now, we know that for gallium arsenide, this is the range that you would expect to get, and this is for gallium nitride. Gallium nitride has a very high output capacitance, and what that means is that its impedance is very low, so most of the current will flow through it, and that gives less of an opportunity to be able to tune the impedances at the load, or at least it has less of an effect. So at the Ka band, the third harmonic load provided by the CDS is close to short circuit, and therefore it's much easier to achieve this Z in 3 equal to 0 in class BJF inverse, whereas to make this into an open would be much more difficult to design, for example in BJF. Now, the second point that we have to remember is that we can achieve a reactive second harmonic because this ZCDS2 here is still a bit away from short, and therefore we can manipulate it. Now, if we had a technology where the output capacitance becomes higher and higher, or we are going to very high frequencies, then it just wouldn't be possible to manipulate this, and you would simply end up with class Bj, irrespective of what you try to do. So BJF inverse would then not be possible. Now here's a technique of how to trade off, another technique of how to trade off efficiency with linearity. And we published this in 2018. And that is by manipulating the current which is flowing through the nonlinear feedback capacitance, or the CGD. This is the nasty part which causes the Miller capacitance. And although theoretically class J and J star are identical, whether you design in the upper half or the lower half, in practice it is not so. So you can always, if you design it in the upper half of the Smith chart, you can see here that for alpha equal to 1, the current adds to the nonlinear current generator, resulting in higher efficiency and P1 dB. So much so that we were able to demonstrate at least 20% increase in efficiency at P1 dB going from class J star to J. So you can see in this region between 51 to 71% the kind of benefit that we were able to show. So this was one of our first amplifiers that we made in the lab, and you can see that it has a fairly high output power, linear output power, P-sat of 41.7 dBm, and with an efficiency of 54.7 at 2.6 gigahertz. These are other comparable works which were also based on the 40010. Now there is a second way by which we can trade off the efficiency with linearity, and this is work that has been recently done by Asha. And what is shown here is by adjusting the second harmonic of the source in such a way as to add, to make it additively, so that the current from the CGT adds to the nonlinear current generator. So this, you can see, it results in an active load despite it being a passive network. And this can further help to improve the performance of a class BJF inverse in terms of linearity. You can see we have a much higher, or not much, but at least a little bit of a P1 dB, but at a much higher efficiency. And the main reason for that is because the voltage is increased here, and the overlap between the current and the voltage is reduced. So this is yet another way by which we can even improve the performance of class BJF inverse. Now we made four prototypes in BJF inverse. So 3 of them were biased at 28 volts, and the last one we thought, we'd push it to 35 volts. And you can see that all of them had efficiency above 70%, excellent gain, and output power. So here is the frequency weighted efficiency of our amplifiers, and the version 1, so they were all designed at about 2.6 gigahertz, but you can see that they had quite a broad bandwidth. 2 of them was greater than 600 megahertz, because you get this ability to design in a 2-dimensional space. And the performance of, to my knowledge, this is the best or the highest frequency weighted efficiency that has been reported anywhere in the literature with the CGH 40010 worldwide. Now, so as I've just mentioned, even though we used simple narrowband designs, we got 3 different bandwidths, 400 all the way 900 and 600, just simply by changing the topology. And so that begs the question, how do we design a broadband amplifier in a contiguous mode? Because you get a much greater choice of impedances in order to be able to achieve your goal. So we used a particle swarm optimization where we not only find the optimal impedances by sort of hitting and trying to restrain our impedances within the target region, but at the same time, we were also able to find the matching network simultaneously without using load pull. And these are the results of our broadband 10 watt part. We had a drain efficiency of between 50 to 70% and output power of 40 to 42.8, again between 12.8 to 14.9, and a fractional bandwidth of about 63%. And you can see here that the IMD, I think, was close to within 20 dBc at up to about 38 dBm of output power. Now, there was this question also as to whether our results are kind of accidental and only restricted to the 10 watt part. So we decided, yes, we'll design a 25 watt part. That also has the challenge that it has a larger device width, so a bigger output capacitance. And you can see this is the 25 watt part that we designed with a bandwidth of 1.1 gigahertz, an average efficiency of 70%, and a plus or minus 1 dB gain variation. If you look at the performance of this with a few other amplifiers that have been reported in the literature, you can see that we are way off the mark. And here are the results of the linearity of that amplifier. So we also found that designing this amplifier in BJF inverse was much easier in terms of CDS than in comparison to BJF. So just to conclude, I hope I've convinced you that it is possible to design harmonically terminated amplifiers. We think we can push it to above 40 gigahertz, but we have to take note of the device cutoff frequency. We need to take note of the device output capacitance and need to make sure that it can be manipulated in order to give us the kind of waveform that we want. We've seen that our amplifiers are very tolerant to mismatch, and this can be a big advantage, especially when we are doing mimic designs with poorly defined PDKs and a big variation from device to device. And our amplifiers are intrinsically broadband in nature. It's much easier to design because you've got such a big area where you can lay your impedances. It's possible to mitigate the trade-off between the linearity and the efficiency by manipulating the current through the nonlinear CGD. I think this is a very useful handle that we have to push our performance even further, and also use the second harmonic source termination as we've just shown. So as a conclusion, I'd like to acknowledge this EPSRC grant where we are trying to look at linearly graded devices for Ka band and above. This is EPSRC funded with Notre Dame in the US, and also an ESA project with Global Invacom. Thank you for your patience and your
Thank you very much, Merlyne. One quick question, anyone?
Hello, thank you very much for your talk. It's very interesting. When I worked on nonlinear PAs, Class E in particular and Class F, I was completely unaware before working on them how their difficulties with them with input power. So you talk about a gain of an amplifier. That gain I found was dependent on the input power. So if you vary the input power, as you would for a traditional linear PA, the gain would vary with the input power. What's the situation? Because you've quoted powers, and it makes sense to run the PA at the maximum power, for intercompression even to get the best efficiency. What's the behavior of a BJF -1 in terms of input power? I mean, if you run it at a lower power.
Back off, yes. We typically design it so that, we get linear power. We would run it at back off. So there isn't an issue with that.
Okay, so you get constant gain with input power. I mean, the gain doesn't vary too much with input power.
So I think, just like I've highlighted these regions of high output power and efficiency, you can also plot a region of high gain, and you can trade off as you wish.
Yeah, it was just that if you wanted to, run a PA like that, I found if I wanted to run the PA like that at lower powers or variable powers, which was the case, for the application I had, you had to have a lookup table to try and predict what the output power was. Well, to not predict, but to determine what the output power was going to be. So
we do the same thing.
Yeah, okay.
Back-of-hand calculations, we do the regions where we want, and then we sort of do a multi-stage in order to get the kind of gain and the specifications that we want. So that procedure remains the same. Yeah. The advantage we have is that, we can decide where we want to sort of, we can plot the regions where we think are of interest to achieve the kind of trade-off we want. So it's the yield which is the benefit, the ease of design, first time correct designs, because all those 3 designs and 4 designs, I mean, they just, right from, without any, and we didn't have batch 2 or anything, they just intrinsically worked and they gave very good performance.
Okay. It's just that I worried then things like AM modulation, if you had to run something which had AM and FM phase modulation,
there's no difference. There's nothing that would affect.
Okay.
Yeah, you can choose linearity. You need to sort of. I can't say that you can completely beat this trade-off. As what we try to do is to mitigate as much as possible, get the best linearity and the best efficiency. That's what this is about, with the least effort.
Okay.
With the least effort.
Okay.
That was important.